In the previous lecture, we have seen what shear force and bending moment mean and how to draw them for the simplest of the cases, which are the cantilever beam and simply supported beam. Now let us take some relatively complex cases. We will use the simple cases to build over the complex cases. The first one is it's a simple case, which is how to draw the shear force and bending moment diagrams for an applied moment. So let's say that I have cantilever beam and I apply a moment M instead of a force on this cantilever beam. Let's say the length is L. So now if I have to draw the shear force and bending moment diagram for this beam, the first step is of course to isolate the beam and draw the free body diagram, and assuming that these are the reactions. So this is the reaction force and the reaction moment. Now we have of course also assumed that these are the x and y coordinates respectively. So I write the equations of static equilibrium and say the sigma Fy is equal to 0. So that directly means that R is equal to 0, which means that there is no shear force in the beam. Because there is no applied force, there is no reaction, so there cannot be any force. Similarly, I write the equation of moment. Let's say this is point A, about A is equal to 0. So that gives me there is an anticlockwise moment M, and there is a clockwise reaction moment which is minus Mr is equal to 0. So that means Mr is equal to M. So the beam will look like this. There is an M and there is an Mr which is equal to M, and there is no other force. Now if I cut a section here and I take this isolated section of length x and I have a moment acting M, there is no force, and I assume that the shear force and bending moment at this section, the cut section, is are SF and BM respectively. Now I write the equation of equilibrium for this section. So sigma Fy is equal to 0. So that gives me SF is equal to 0. There is no shear force in the beam. Similarly, I write sigma M. Let's say this point is A is equal to 0. Moment about A. Now there are three moments. First is the BM. Second is the shear force multiplied by X. And third is the reaction. Now reaction is minus M because it is acting at the in clockwise direction. So the sum of them is 0. SF is equal to 0. So that directly is taken out. So BM is equal to M. So at any section, the moment, bending moment is equal to the applied moment. So if I have to draw the shear force diagram, it is just the straight line at origin. There is no shear force. SFD, SF is equal to 0. And if I have to draw the bending moment diagram, it is Y and this is X, and it is a constant entity. This is M. This is L. This is bending moment diagram. Now this is also a very simple case. Now let's take the other simple case, which is what happens if I apply shear force, a concentrated moment to a simply supported beam. Now this is the case for simply supported beam. So I have this this is the roller support and this is the fixed support, pin support, and I apply a moment, a clockwise and anti-clockwise moment, let's say at a point A from the left end. and this total length is A plus B. Now, you see, this case is vastly different than the case of either the cantilever beam with moment alone or the simply supported beam with a force alone, and we will see why. Now, in this case, I I isolate the beam again and I provide the reactions. So I say this is RA and this is RB, and this is the moment which is applied at some point M. This is A, this is B. Now over here, if I have to write the equation of equilibrium to get RA and RB, I will say sigma Fy is equal to 0 will lead me to say RA plus RB is equal to 0, and that's the right thing because there is no applied force, hence the sum of the reactions must be equal to 0. Similarly, I will say M about A is equal to 0. This is point A and this is point B. That leads to the first moment, which is M plus RB into A plus B is equal to 0, which means RB is equal to minus M upon A plus B and RA is equal to M upon A plus B. You see why this is coming, because if you see the sense of moment, it is trying to, this moment is trying to make the beam like that, correct? And the support here is trying to pull the beam down. That's what is happening at B, and that is the reason why it is minus, because it is pulling the beam down, it is down, while at A this beam is trying to go down, so the support is pulling it up. This is a support. So RA is a positive entity and RB is a negative entity, and they are equal in magnitude, and that's right because the moment is a free vector, it can be applied anywhere, it doesn't matter, and the force will be equal and opposite because the sum has to be equal to 0. Now with this information we draw the reactions again. So RA, that is equal to M upon, let's say L, where L is equal to A plus B, and this is RB, that is equal to M upon L, but the direction is inverted now, and this is M. Now I cut the beam here at some location X, not here, sorry, here, this is A. So I cut the beam at some location X where RA is applied, and I assume that the bending moment and the shear forces are acting like this. Over here, now sigma Fy is equal to 0 leads to SF equal to, or rather SF plus RA equal to 0, which means SF equal to minus M upon L, and at the same time the moment about A is equal to 0 will lead to Bm plus SF into X is equal to 0, which means Bm is equal to minus SFX, which is nothing but M upon L into X. So at X equal to 0, Bm is equal to 0, and at X equal to A, Bm is equal to M upon L into A. Now please see this equation carefully. SF is a constant entity, it is minus M upon L till X is less than or equal to A, which is the point of application of the moment. Now if we have to draw the bending moment diagram for the other half, which is beyond the point of application of the moment, what we do is we take a cut section which is beyond this point. We take a cut section here. So we take a cut section which is like this. The moment is applied here, M, this is point A, and then we take section X, and this is RA, that is equal to M upon L. Now if we write the shear force diagram, shear force and bending moment equations for this section, sigma Fy is equal to 0 will lead to the same thing which was there in previous case, which is Sf plus Ra is equal to 0. That means Sf is equal to minus m upon L. Now the moment on the other hand is a vastly different story now. Now let us see what moment is. So moment will be equal to, now there are three moments acting now. There is the Bm plus there is a applied moment M plus the shear force multiplied by A plus X, that is equal to 0. So that leads to Bm is equal to minus M minus Sf into A plus X, that is nothing but minus M plus M upon L into A plus X. Now at X equal to 0, which is the place where moment is applied, Bm is equal to minus M plus M upon L into A, which is nothing but, we can take L as denominator and it will be M upon L A minus L, which is nothing but M upon L into minus B. You see, A minus L is nothing but L minus A minus, or minus of L minus A, which is nothing but minus B. So this is the bending moment at the point where moment is applied, but when we go from the right hand side. Now at X equal to, now X will be equal to B, the moment, bending moment is equal to minus M plus M upon L into A plus X will be L, so that will become 0. So if we draw the shear force diagram and bending moment diagram using this information now, the shear force diagram will look like this. Shear force is a constant and it's a negative quantity, so it is like this. This is negative minus M upon L. This is the SFD. While the bending moment diagram will be actually quite different. So the bending moment diagram looks like this. It increases from 0 to M upon L into A till the point of application. Then at the same point drops down to minus M upon L into B, which is this number, and then goes to 0. So this point is M upon L into A, and this is minus M upon L into B. You see, this is the kind of it's a very what should I say, peculiar case of bending moment diagram, but it's actually quite clear. The point where we are applying moment, now you see the difference between these two, this height is equal to M. You can just add the two numbers, M upon L minus MB upon L. So if you add these two numbers, it will become M upon L A plus B, which is nothing but M. This shift from this point to this point is because of the moment applied. So this is a very important case in my opinion, and it gives a lot of insight into how to draw the shear force diagrams and bending moment diagrams for cases where moment is applied. Moment application is something which is not very clear intuitively, because we don't know what how to apply moment as a pure moment. Moment is always applied as a couple, which is like two forces acting in equal and opposite directions separated by a very small distance. Now let's see how to draw shear force and bending moment diagrams for some cases which are composites, in the sense that there are forces as well as moments acting. So let's take a very simple case first, wherein we have a simply supported beam, and it obviously is like this. So we have a simply supported beam, and this is a pin, and that's a roller. And let's say we have a concentrated force P acting at the center. It's like L by 2, and this is L by 2. But besides this, we also have one moment which is acting like this here, M. Now let's see how to draw the shear force and bending moment diagram for this case. This case is a very what should I say, good case, because it gives a lot of insight into how to draw the shear force and bending moment diagrams for composite cases. Now we isolate the beam and provide reactions here. So this is, as I say, this point is A and B. So this is RA and RB, and this is P, and this is M. Now I write sigma Fy is equal to 0 and assume directions are y and x like this. So this gives me Ra plus Rb is equal to P. And similarly, sigma M at A is equal to 0 will give me minus PL by 2 plus M plus RB into L. That gives me is equal to 0. So that gives me RB, that is equal to PL by 2 minus M divided by L. This is by L. So this is nothing but P by 2 minus M by L. Now please relate this with the previous case. The moment reaction at A, the reaction because of the moment alone at A, this is point A, was M by L. And now we have a reaction because of the force. So the force and the reaction because of the force and reaction because of the moment, they are together now. Now this minus is coming because the moment is trying to put this point down. Quite frankly, I think I have done something wrong here. I think it has to be plus. So I just take the case again. So this moment about A, that will be RB into L is counterclockwise, M is counterclockwise, and PL by 2 is clockwise. So, oh, I'm sorry, this is RB, right? So this is RB here, is right. So RB, of course, the moment is trying to take the beam away up like this, while P is trying to put it down. So both of them are, negating each other. But RA will be nothing but P minus RB, so that will be equal to P minus P by 2 plus M by L. So that is equal to P by 2 plus M by L. Now over here, I just write it again. RA is equal to P by 2 plus M by L. Over here now it's very clear. RA is having additive effect, or rather the moment and the force are adding each other, while at P they are negating each other. Now let's draw the shear force and bending moment diagram for this case. So we take a section here at a distance of x, and I isolate that section. So I take this portion, this is point A, this is RA, which is nothing but P by 2 plus M by L, and I assume that the shear force and bending moments are called BM and SF, and this is point X, or this is distance X. Now I write the equation of, okay, this part is separate. Now I write the equation of equilibrium for this portion and say Fy is equal to 0. That leads me to SF plus P by 2 plus M by L is equal to 0. So that means that SF is equal to minus P by 2 minus M by L. Similarly, I write moment about A is equal to 0. That leads to BM plus SF into X is equal to 0. So BM is equal to minus SF into X, which is nothing but P by 2 plus M by L into X. Now let's see how this varies over the length from 0 to L by 2. So at x equal to 0, Bm is equal to 0, which is right, because at point A there is no moment reaction, because it's a pin support. There cannot be any moment reaction, so there cannot be any Bm also. So it is 0. At x equal to L by 2, Bm is equal to, now put the value of L by 2 here, x here, so that will become P by 2 plus M by L into L by 2, which is nothing but PL by 4 plus M by 2. Now you see this equation carefully. What this tells is, at the center point where P is applied, had there been only the force, the bending moment there would have been P into L by 2 into L by 2 upon L, because it is PAB upon L. So from that it would have been PL upon 4. But because there is a moment also and it is at a center, so half is shared there, so it is adding up. Now, so for this portion of the beam, this is the way it behaves. So the shear force is a constant, which is nothing but the sum of the half of the applied force and the moment reaction, and the bending moment is again the same thing. Now let's see what happens if we take the section here. So at that section we have P applied and M applied, and at this point we have RA, which is nothing but P by 2 plus M by L, and I take SF and Bm to be the shear force and bending moment at that section. Now that distance is x and this is L by 2. Now I take the equilibrium of this and say sigma Fy is equal to 0. That means there are now three forces, SF minus P plus P by 2 plus M by L is equal to 0. That means SF is equal to, this will go here, so that will become P by 2 minus M by L. Similarly, the moment at A is equal to 0 will means Bm plus SF into x plus L by 2, SF is this SF now, minus P into L by 2 plus M is equal to 0. So that will mean Bm is equal to PL by 2 minus M minus SF into x plus L by 2, which is nothing but PL by 2 minus M minus SF. Now SF is P by 2 minus M by L. So I just replace these quantities here. I expand the bracket, so that becomes into x minus P by 2 minus M by L into L by 2. There is nothing but PL by 2 minus M minus P by 2 minus M by L into x minus PL by 4 plus M by 2. So that means I can subtract this and this, it becomes PL by 4 minus M plus M by 2 is minus M by 2 minus P by 2 minus M by L into x. Now at x equal to 0, which is at the center, Bm, when we come from the right side, is equal to PL by 4 minus M by 2. Now you see this, compare this with this quantity. The sign of moment is inverted. You remember from the case of pure moment on simply supported beam, this is the same thing. Now at x equal to L by 2, which is this point, Bm is equal to, I just put L by 2 here, so that becomes PL by 4, PL by 4 is cancelled out, M by 2 plus M by 2, so it becomes 0. So now I draw the shear force and bending moment diagram. So the shear force diagram is like this. It's for this portion, for the left portion, it is this much. It's a constant quantity, negative. Then for the right hand side it is this much. But for this, we should know what is the value of m to be clearly able to place whether this point is above or below the x-axis. Let's assume that p is a very high quantity, so it goes up and it comes down like that. Now let us draw the bending moment diagram for this. Bending moment diagram is like this. So it starts from 0 and goes to a very high number, which is like this, then suddenly falls down and goes down to 0 again. So this is upon PL upon 4 plus m by 2. This is PL upon 4 minus m by 2. Now of course, if m is equal to PL by 2, this quantity will be equal to 0 if it is the case, and this quantity will become equal to PL by 2. Similarly, if m is PL by 2, then let's see what happens to this one. This is equal to, this point is P by 2 plus m by L minus, and this point is P by 2 minus m by L. Now if m is PL upon 2, this will become PL upon 2, so this will become 0. All this will become P. So this is how we build up the cases which are composite. Composite means which are cases where where different types of loadings are coming together.